In this talk, I will introduce the paper, Causal Direction of Data Collection Matters, Implications of Causal and Anticausal Learning for NLP. This work is presented at EMNLP 2021. The paper is a joint collaboration among Max Planck Institute for Intelligent Systems, ETH Zurich, University of Cambridge, UCL, and IIT Kharagpur. I am Zhijing. I also want to thank my wonderful co-authors, Julius, Jingwei, Tejas, Ayush, Mrinmaya, and Bernhard. First of all, let's look into the concept of causality. So as scientists, we usually observe a lot of data in the world. And then to like one step further, we want to infer the causal graph in the world. So there are two forms of it. One is that by scientific discovery, we might find some variables causing some other variables and put them into our science books. And the other form, alternatively, is by recovering the data generation process. So this alternative way to understand causal graph is that some variable are generated first, and then they causes the generation of some other variables, such as in the bivariate case, x causing y, is that first x is independently generated, and then following x, y is generated, given the value of x. So especially in this paper, we look into causality as data generating process and introduce the various properties of it. So let's dive into an NLP example. So we choose one example from machine translation, but it also applies to other NLP tasks. So for machine translation, let's say in this example, we have a German original text, and then it's translated into English. So when observing the data, we can see that there are some footprints of the translator's translation process. So first, they choose to use the cleft sentence to express emphasis, like it is. And then they also choose to put the word today to the beginning of the sentence instead of middle or the end. Moreover, they connected the two sentences, which are originally two separated sentences, into two clauses connected by and. That's why. So based on this data, we can observe that models learning from this data, from original German to translated English, will be likely to pick up the habits of English translators who contributed to this data, and also general linguistic phenomena of English translation needs from German, such as simplification. So more formally, we want to sort of introduce this notion of data collection direction and modeling direction. So in the data collection stage, we usually have we usually collect one of the variables first, and then based on the first variable, we collect the second variable by a human annotation process. And then in the modeling stage, there can be two ways, like two modeling directions. One is from the original variable to learn the second variable. And the other is from the second, the generated variable, to recover the original one. So the first task will be the same as the data generation direction, and the second task will be opposite to the data generation direction. To give them formal names, according to Schölkopf et al. 2012, the first is called causal learning, to learn a task the same as the data generation direction. And the other one is called anticausal learning, to learn a task that is opposite to the direction of data generation. So the key question in this paper is that, given the two concepts, does this task nature matter for machine learning? And the answer is yes. There are existing literatures reporting some results similar to this to some extent, but there lacks a formal concept for them. in this paper, we introduced this vocabulary, especially in the context of NLP, and also show some theories of like related to this concept so that it can give insights to future practices. So the three key messages of our paper are to answer this question, does causal or anti-causal learning matter for ML? Yes, it matters. And the second is how does it matter? We will show two cases. One is a case of semi-supervised learning, and the other is a case of domain adaptation. So, and third, we will show what does it mean for future NLP practices. We suggest causality-aware data collection and modeling. So now let's dive into this principle of independent causal mechanism that explains the difference between causal and anti-causal learning. So we will, before formulation, we will introduce the notations. So in the data collection stage, first we have a variable cause, C, and then we get the variable effect, which is E. So the causal mechanism is to generate C to E by a function f with certain like noise in the function, so that it becomes a probability distribution. And then in the modeling stage, for the two tasks, causal learning and anti-causal learning, causal learning learns the f, which is the same as the original data, like causal mechanism. And the anti-causal learning learns a G, which is like reverse of the data generation mechanism. So, and the independent causal mechanism, ICM, suggests that the causal mechanism is independent of the cause C for a given task. More specifically, we formulate it by algorithmic information by Kolmogorov complexity. So Kolmogorov complexity describes the shortest computer program to describe a phenomenon. It's more an idealized concept to formulate many of the concepts. Here we will have the Kolmogorov complexity of the joint distribution of C and E. So like sort of we can think of it as the shortest description to encode this joint distribution can be decomposed to two elements. One of them is to the description of the distribution of C, and the other of them is the description of this causal mechanism from C to E. So this decomposition is a nice decomposition because there's no shared information by the ICM principle here. And then if we do it in the other way, like describe the effect distribution first, and then describe the reverse mechanism, then this will very likely to cause a much higher complexity because there might be redundant information among the two terms. In terms of experiments, we approximate this Kolmogorov complexity by minimum description length. And we collected machine translation data and proved showed the trend on machine translation data with clear causal direction. So based on this ICM, we aim to convey the following takeaways. One is that alignment with data generation process matters because it'll make the learning task causal or anti-causal. The other takeaway is that for semi-supervised learning, it's better to use for semi-supervised learning, anti-causal learning will show more improvement than causal learning, versus for domain adaptation, causal learning will show more improvement than anti-causal learning. To give more details, for semi-supervised learning, the setting is usually that we have the cause and effect pair, and semi-supervised learning assumes additional input data. So if we're learning the causal way, then the additional input data will be C prime. And then C prime by the ICM should share no information with the causal mechanism here. Whereas if you're learning in the anti-causal direction, then your additional input data will be additional unlabeled effect. And the effect will be very likely to share information with the inverse mechanism. And in the other case, in the domain adaptation setting, we are specifically concerned with covariate shift, where we have the original domain C and S plus another domain like C and E and another domain S. In this domain, we will have CS and ES. Here, the cause, there will be covariate shift in terms of the cause of the original domain differs from this new cause. And then if we're doing the causal learning task, then it's very likely that the causal mechanism stays the same across domains. So with this additional domain data, the causal learning should improve more than the inverse mechanism, which shifts in the domain. What does this mean practically? We suggest that when collecting data, please annotate the causal direction between the input and outputs. And second, when modeling, feel free to consider the causal direction as an important piece of information. There can be some potential suggestions, such as add the tag cause and effect to the input and output data, add a task prefix to trigger different inference behavior for causal and anti-causal learning, or limit some training methods only to one of the directions. These are some tentative suggestions inspired from similar works, but we also strongly encourage more innovative future work. So to summarize, we will end with the re-emphasis of the 3 key messages. The task nature, causal versus anti-causal matters for machine learning practice. And especially in the semi-supervised learning and domain adaptation, it shows a clear difference. And lastly, we suggest causality-aware data collection and modeling. Thank you for listening.